Hello everyone, I'm Xinyu Wang from Shanghai Tech University. I would like to share our work on AACL 2020. The title is Signal Order Neural Dependent Parsing with Message Parsing and End-to-End Training. Recent work introduced signal order inference into their parser and achieved state-of-the-art performance. In this paper, we apply a previously proposed signal order semantic dependency parser to syntactic dependency parsing. To meet with the constraint of head selection in dependent parsing, we add some simple modifications. We also make two interesting observations from our empirical study. First, it is a common belief that contextual word embeddings such as Elmo and Bird already conveys sufficient high-order information that renders high-order parsing less useful. But we find that second-order decoding is still helpful even with strong contextual embeddings like Bird. Second, while previous work found that incorporating the head selection constraint is helpful in first-order parsing, we find that a better loss function design and hyperparameter tuning, both first and second-order parsers without head selection constraint can match the accuracy of the parsers with head selection constraint and even outperform the latter when using BERT embedding. Our structure is a second-order dependency parser. We score the first-order and second-order paths and use mean-field variational inference to approximately inference the highest dependency tree. We fix the inference step of the algorithm and forms an end-to-end neural network to calculate the probability of potential heads of each word. For the classification, we categorize different kinds of graph-based dependency parsers based on their structured output constraints according to the normalization for output scores. We first introduce single approach. A single approach places no structure constraint, viewing the existence of each possible dependency edge as an independent binary classification problem. Our single parser is an end-to-end neural network derived from message parsing inference on a conditional random field that encodes the second-order parsing problem. It is a single approach because of the lack of structure constraints. Here is the factor graph of the single approach. In the figure, each edge represents a variable, taking the node 1, 2 as an example. It represents the variable of the first word Z to the second word where. The node connects a unary factor which represents the score of the edge itself. The connection between the node and the sibling and the grandparent factors represents the second-order paths. The second-order path connects to other nodes that form the second-order relationships with the node 1, 2. While the single approach uses Boolean random variables to represent the existence of possible dependency edges, a local approach defines a discrete random variable for each word specifying its dependency head, thus enforcing the head selection constraint and leading to different formulation of the message parsing inference steps. The message parsing inference formula for single and local approach are listed here. For each step, the message passed between the neighboring edges. A certain edge formulates the sibling and grandparents relationships with the neighboring edge. At each inference step, both the single and the local approaches normalize its approximate distribution Q. The single approach normalizes the probability of the edge existent at each step, while the local approach normalizes the probability distribution of its dependency head. For the approach to output valid path trees during testing, we run maximum spanning tree based on the posterior edge probabilities predicted by these approaches. We first conduct our experiments on PTB and CTB. We use single 1-0 to represent first-order single approach, local 1-0 to represent the first-order local approach, single 2-0 to represent the second-order single approach, and the local 2-0 to represent the second-order local approach. The table shows the unlabeled attachment score and labeled attachment score of all the approach as well as the reported score of previous state-of-the-art approaches on these two datasets. It can be seen that without BERT, our local 2.0 approach achieves the state-of-the-art performance on CTB and had almost the same accuracy as the very recent work of Zhang et al. On PTB, which is a signal-order tree CRF parser. With BERT embeddings, the local 2.0 performs the best on PTB, while the single 2.0 has the best accuracy on CTB. This table shows the results of 5 approaches on UD in addition to PTB and CTB. We additionally use a previous state-of-the-art graph-neutral network parser as the baseline, representing as GNN. We make the following observations. First, our second-order approaches outperform GNN and the first-order approaches with BERT and without BERT embeddings, showing that the second-order decoders are still helpful in neural parsing even with strong contextual embeddings. Second, without BERT, local approaches slightly outperform the single approaches, although the difference between the two is quite small. When the BERT is used, however, single is clearly outperform local, which is quite interesting and warrants further investigation in the future. Third, the relative strength of local and single approaches vary over the tree banks, suggesting the importance in the head selection constraint. We evaluate the speed of different approaches on a single GPU. As shown in the table, our local approach and the single approach have almost the same speed. Our second-order approaches only slow down the training and the testing speed in comparison with the first-order approaches by 23 and 12% respectively. They are also significantly faster than the previous state-of-the-art approaches. Our local 2.0 approach is 1.2 and 2.3 faster than GNN in training and testing, and 2.4 and 2.9 times faster than the second-order tree CR proposed by Zhang et al. In terms of the time complexity, our second-order approaches have a time complexity of O(n) cubed, while the time complexity of the GNN is O(n) squared times d. The hidden size d is typically much larger than the sequence length n, and the decoder of Zhang et al. Has a time complexity of O(n) cubed as well, but it requires sequential computation over the sentence, while our decoders can be parallelized over the words of the input sentence. In conclusion, we propose second-order graph-based dependent parsing based on message parsing and end-to-end neural networks. We modify a previous approach that predicts dependency edges independently and also design a new approach that incorporates the head selection structured constraint. Our experiments show that our second-order approaches have better overall performance than the first-order baselines. They achieve competitive accuracy with very recent state-of-the-art second-order graph-based parsers and significantly faster. Our empirical comparison shows that the second-order decoders still outperforms first-order decoders even with BERT embeddings, and that the usefulness of the second head selection constraint is limited, especially when using the BERT embeddings.